So today we're going to look at some properties of definite integrals and some ideas about antiderivatives. We looked at this antiderivatives just a very little bit the other day, just looking at what happens if you have a constant function and you want to find its definite integral. But here are some other properties. So the first property, the integral from a to b of f of x dx is equal to the opposite of the integral from b to a of f of x dx. By the way, there are times when you should think of that as the opposite and not as negative. Because what if the first definite integral was negative to begin with? Right? Then the second one would just be the opposite. It would be positive. Notice that all we've done there is changed the limits of integration from a to b to a. So if you're working right to left and then you switch to working left to right, you change the sign on the integral but not the value. My all-time favorite one, the integral from a to a of f of x is 0. Because how much area is in between your two hands when you squish them together like that?
0.
None. Yeah. Okay. One thing that we can do, and this is sort of like one of the properties of taking derivatives, is that if we have the integral of a constant times a function with respect to x, we can factor that constant out. In other words, we're going to keep the constant multiple, just like we keep the constant multiple when we take a derivative. Also, just like with taking derivatives, if we have the sum or the difference of two functions, we can do those each individually, just like what we do with derivatives. Here is an interesting one. The integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. Everybody is happy with this as long as a is smaller than b, which is smaller than c. I'll show you just a quick sketch of that, and then I'll show you how it doesn't have to be that way. So if you've got y equals f of x, and this is a, and this is b, and this is c, everybody's happy that the integral from a to b, which is this area, plus the integral from b to c, is equal to the integral from a to c. Everybody's happy with that. But it doesn't have to be that way. What if a was here, and b was here, and c was here? Is it still true?
Yes.
Why?
Because from b to c is negative.
Exactly right. The integral from a to b would be all of this. Then the integral from b to c would be the opposite of this area, which would leave you through the area from a to c. People tend to think of, when they first learn it, they're like, oh yeah, because b is in between a and c. It never says that. In fact, it never even says that a is the least. The order is unimportant. Okay? What is important is that these two match. Nothing else really matters in that. What's important is that those two match. Something that comes into sort of the more theoretical side of things is that the minimum value of f, and I should put on the closed interval from a to b, times b minus a is going to be less than or equal to the integral from a to b of f of x dx, which in turn will be less than or equal to the maximum value of f on the closed interval from a to b. So please add that, times b minus a. Maybe even add a dot so that you know it's times. And again, if you want to think about it in terms of area, basically what they're saying is the least height of f times the width of the interval is going to be less than the integral, which will be less than the greatest height of the function times the width of the integral. Okay? And another one that I think is relatively straightforward, if f of x is greater than or equal to g of x on the closed interval from a to b, then the integral from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. It's the same width, but f is either higher or equal to g of x, so it's got greater area. All right, so here are some problems that some of you can do, some of you cannot. And that's part of the question on this is, do you know which ones you can do and which ones you can't? So we're given all this information. The integral from -1 to 1 of f of x dx is 5. The integral from 1 to 4 of f of x dx is -2. The integral from -1 to 1 of h of x is 7. Given those three pieces of information, some of these you will be able to find, some of them you will not be able to find. Let's take a look. So what about the integral from 4 to 1 of f of x dx? Can we find that? Yeah, it's just going to be the opposite, and you wouldn't have to write this out, but I'm going to. It's going to be the opposite of the integral from 1 to 4 of f of x dx. So that's the opposite of -2, which is +2. Well, what if I want the integral from -1 to 4 of f of x dx? Can I do that? Yeah. This will be equal to the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. So it'll be 5 plus -2 is 3. What about the integral from 0 to 1 of f of x dx? Pardon? I just didn't hear. Thought someone said something. Pardon?
I don't think so.
Yeah, you can't. Unless you know that f is an even function and you could split this one in half. But that is a fairly common mistake people will make. They'll say that it's 2.5 because it's half of the distance from -1 to 1. But unless we know it's an even function, we can't do that. So this is not possible. For the next one, we want the integral from -1 to 1 of 2 times f of x plus 3 times h of x, all dx. No. It had to be Irfan, didn't it?
Yes.
So this would be equal to 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. So that'd be 2 times 5 plus 3 times 7 is 31. Probably the most missed one, at least at first, is number 5. You know, like, okay, how hard can that be? Well, if you don't think about splitting it into two integrals, people make a mistake. I want you to guess what the mistake they make is. But if we split it, it would be the integral from -1 to 1 of h of x dx plus the integral from -1 to 1 of 3 dx. So that would be 7 plus, that's the constant rule, it's 1 minus -1, is 13. What do you think students might do on that would be a mistake? Pardon?
They would do 7 plus, like, integral of 1 to 8.
They just do, yeah, they do the integral part for the h of x, and then they just tack on a plus 3 at the end.
What else would you do?
What they are doing that is incorrect is they're doing this, the integral from -1 to 1 of h of x dx plus 3,
That's no.
right? Which is not the same thing. And what about the integral from -2 to 2 of h of x dx? Is it 14?
We don't know what H is.
No.
Yeah, we have no idea what this does. This is, again, not possible. Certainly. All right, page 2. So going back to very basic ideas, if we know the area of a rectangle and we know its base, we can find its height.
Wow.
Ooh, man.
That's tough.
It's also, you just took a test on this.
Yeah, you just took a test on this?
On this specific topic.
Oh, you want one on this. I see. So the height would be the area divided by the base. Is that what you were saying, or did I miss something?
No, never mind.
Is this something you did in physics or something?
Never mind.
Okay, sorry. I just felt like I missed something. So, what if the top of the rectangle is a curve? So it's no longer a rectangle. That's why I put rectangle in quotes. And we divide the area by the base.
Uh-huh.
What we end up getting is the average height. That makes sense?
It sure does.
Okay? So if the curve is described by an integrable function, then the average of f is equal to the integral from a to b of f of x dx, that's the area, divided by b minus a, that's the width of the base. And if f is continuous on the interval from a to b, then at some point c in that closed interval from a to b, the average value of f will be equal to f of c. Okay, that kind of makes sense?
Yeah.
So this is how you can find the average value of a function on an interval when that function is not just a line. So for example, find the average value of f of x is equal to 7 minus x squared plus x on the closed interval from 0 to 3. Where on the interval does f take on this value? Okay. So the area, let's just go ahead and do it all at once. The average value of f will be the integral from 0 to 3 of 7 minus x squared plus x dx over 3 minus 0. Before we go on and calculate that, quick question, what do you think students may confuse this with? Average rate of change. Two entirely different things. Average rate of change, f of b minus f of a over b minus a. Average value of the function, the area given by the integral divided by b minus a. Okay? You don't know how to do that yet. You probably do. Did you learn that in physics? No? Okay.
We don't
Wow.
Wow.
don't think so.
Maybe Mr. was like trying to explain this to
Yeah,
us. and we're
kind
like,
of.
no.
My brain probably wasn't working.
So we can do this pretty easily.
Oh, yeah, your calculator does it for you.
Oh, that's awesome.
Forgot about that.
Your calculator.
Yeah, remember I told you that the that's one of the things you're required to know.
Oh, that would be helpful.
Yeah.
Yeah, none.
It's like another Dylan.
So 7 minus x squared plus x with respect to x over 3 minus 0. So the average value of the function is 5.5. Then it wants to know, well, where does this occur? Okay, well, let's see. We want, where does 5.5 happen on 7 minus x squared plus x? So it'd be 0 is 1.5 minus x squared plus x. I have no desire to try and figure that out by factoring or by the quadratic formula.
Looks fun.
And since I've already used the calculator, I'm assuming this is a calculator active problem. So 1.5 minus x squared plus x. I'm going to set my window to go from 0 to 3 because I don't care where it happens outside of that. And I'm looking for zeros. So I'll look between -1 and 1.
Between 1 and 2.
Yeah, somewhere between 1 and 2.
Let's say 1.8.
Lily, you making a guess today?
1.8.
I think 1.85.
1.8.
1.87.
A little closer to 1.9.
1.82.
Yeah. You are.
Now, I do want to show you something real quickly. I'm going to do this on Graphmatica instead. If I graph this function on the interval from 0 to 3, I probably don't need all that room, but that's okay. So 7 minus x squared plus x equals y. Looks like that. If I were to find where this is 5.5, let me erase the stuff that's on here. That's 5. 5.5 right about there. And I go over. Did we get about what we wanted? What was it, 1.8 something? Okay. The interesting thing is if I continue to extend this across here, what that should mean, if I have done it correctly, is that this area should be equal to this area. It's a little bit hard to see because this one is wider than that one. Okay, but that's the idea behind the average value of a function. So that's one of the things you can use an integral for. So let's look at a couple of other things. Consider a plane flying at a constant ground speed of 120 miles per hour from noon until 6 p.m. What does the integral from 1 to 4 of 120 dt tell us?
How far plane travels?
How far what?
Plane travels.
Uh-huh, give me more.
At 6 p.m. Well, from noon to 6.
No, look again, be careful.
One.
Oh.
That's tricky.
Uh-huh.
How far the plane travels. In miles, you got to give units. From 1 p.m. to 4 p.m. So much as it is in AP Stat, context is important. All right, so how about this? If S of t is the position of the plane at any time t, between time 0 and 6, then its velocity is S prime equals v of t, right? What does the integral of S prime of t from 1 to 4 dt tell us? Yeah. So in physics, what does you call that distance that it's traveled? The displacement. The displacement would be S of 4 minus S of 1. So again, this is that. It's how far the plane travels, right? So notice that if the integrand is the derivative, is a derivative of something, then if I was able to undo that derivative and evaluate the function taking the difference, I would find the quantity that I wanted. So think about it this way. If we interpret the integrand as a rate of change of f of t with antiderivative capital F of t, then the integral from a to b of f of t dt is equal to capital F of b minus capital F of a. This is big, important, huge idea. So that will allow us to evaluate this integral using an antiderivative. Because if f of t, now we'll call it x because it's x here. If f of x is sine of x, I should just start over. If f of x is sine of x, then what is an antiderivative? What can I take a derivative of and get sine? Yeah. What if I had negative cosine of x plus 17? Would its derivative still be sine of x? I'm going to use that one. It's not going to change my answer in the slightest. The integral from 0 to pi of sine of x dx then is going to be capital F at pi minus capital F at 0. So that will be the opposite of the cosine at pi, plus 17, minus the opposite of the cosine at 0, plus 17. Cosine at pi is
Negative 1.
-1. So this is 1 plus 17 minus cosine at 0 is 1. So this will be -1 plus 17. Do you see why the 17s don't matter? They're going to subtract out of this. It's 2, which we did the other day. I said we would show you why it was. This is why. It's very interesting to me that with a width from 0 to pi and a weird curve like sine of x, that the area underneath it is 2. It's a tough room today. All right. So that's all of that. I do want to, though, spend a little bit of time. I know we don't have a ton, but I do want to show you this deal with Riemann sums. I got to be able to find it, though, first, real quick. Definite integrals. I don't know where it is. I have a copy of it, though. Must be in here someplace. Notes, 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 quiz, Riemann sums, trapezoidal approximations. Weird. Okay.